that is local anesthetic, and this local anesthetics is from unit 5.2. Audible?
Yes.
Okay, we will start with the unit 5.2 local anesthetics, as we are considering that is a part of your unit 5. In this local anesthetics, we are talking about SAR of local anesthetics, some of the chemical classification of local anesthetics, that is benzoic acid derivatives. Examples are cocaine, hexylcaine, meprilcaine, cyclomycaine, piprocaine. Likewise, second class is aminobenzoic acid derivatives. Lidocaine, similarly, it is known as anilide derivative, and some of the miscellaneous class of the drug. Before we start with this and local anesthetics, we will have to first see the structural features and what are their properties. Two important chemical properties of local anesthetic molecules that determines its activity. The first one is a lipid solubility. Increase the extent of substitution on aromatic ring or amine group. And second is the ionization constant that determines the proportion of ionized and non-ionized form of anesthetics. So when we talk about the lipid solubility determines the potency, plasma protein binding, and duration of action of local anesthetics. When we see this table, it has shown some points like procaine, lidocaine, and tetracaine, three molecules, and they are compared here with lipid solubility, relative potency, plasma protein binding, and its duration of action. When we consider procaine, a simple molecule procaine, lipid solubility they have considered 1 and relative potency is 1. The plasma protein binding is 6. Now the duration of action is 60 to 90 minutes. Local anesthetics are weak bases, and generally the proportion of this weak bases, that is RNH2, it is and its salt, that is RNH3 plus. It depends on the pH and pK of amino group. Therefore, the Henderson-Hasselbalch equation for the weak bases are like here. pH is equal to pK plus, and here we are talking about the bases. Therefore, it will be log of base divided by salts. Example is given here. Calculate the proportions of free base and salt form of tetracaine. Now tetracaine pK is 8.5 at pH 7.5. As per the formula, we have tried to calculate the proportion of free base and salt form. Therefore, the salt and base to salt form ratio, it will be 1:10. This is one of the example that we considered for the calculation of dissociation. Therefore, the 10 times more potent drug is ionized than the non-ionized form at physiological pH. This is how we have to calculate the proportions of pre-bases. Both pre-bases and ionized forms of local anesthetics are necessary for the activity. A local anesthetic enters the nerve fiber base as shown in the figure, and the cationic form block the conduction by interacting at the inner surface of sodium channel. You have to remember one thing: only the neutral compounds can cross the barriers. There are very rarely possible that only the ionic and cationic forms they can cross the barriers. But here, if you look at the figure, one of the neutral free base that is converted into diffusible form, and it forms with a simple nitrogen. That diffusible form can cross the membrane here. You can see this transfer of this diffusible form, and again when it comes inside the membrane, proton binds with the diffusible form and it again activate the bases. So if we compare this particular diagram with the sodium channel here, similarly the diffusible form of local anesthetics that enters through this sodium channels, and as soon as it enters into the cell, the ionized form of that local anesthetics that can activate the sodium channels. This is important for the activity of the free bases and the local anesthetics. Again, if we compare the local anesthetic having a lower pK value, it is having more rapid of action, and almost it is considered more unchanged form of more rapid diffusion to cytoplasmic side of sodium channel. As again 3 examples are given with the pK, and they have calculated the percentage of free bases at pH 7.7 and the onset of anesthesia. As the first drug in this table is lidocaine, almost having a near pK near to neutral, that is 7.9. But if we try to calculate the free base percentage free base at pH 7.7, it is almost 25. And as the free base concentration, ionization concentration is higher, the onset of anesthesia will be faster. The next example is bupivacaine. The pK value is 8.1, and if we try to calculate the percentage free base at pH 7.7, it is 18. As compared to lidocaine, it is somewhat lesser, so it acts on the onset of anesthesia. The onset of anesthesia for bupivacaine is 5 to 8 minutes. Then our third drug molecule in the table is procaine. Procaine, because of the availability of nitrogen, the pK of the drug molecule is almost towards the basic compound, that is 9.1. If we compare the free ionization of the free base at pH 7.7, it is 2. And if we compare with the other two drugs, the onset of action, onset of anesthesia will be more as compared to lidocaine and bupivacaine. Therefore, the dissociation constant as the percentage of free base we have to consider as an important criteria for the action of local anesthetics. As the table here, it suggested the local anesthetic with a lower pK have a more rapid onset of action and more uncharged form, a more rapid diffusion to cytoplasmic side of sodium channels. Then we'll see the mechanism, as we have already covered the mechanism, how this free base diffusible form enters into the cell and it activates the sodium channel. Here also it is somewhat broader aspects of this inhibition of inhibition of sodium channel by local anesthetics. Here the sodium channels are inhibited by local anesthetics as shown in the neurons, and neuronal cells are playing important role for the inhibition of this sodium channels. Let us consider now the SAR points for this local anesthetic. As shown here in this, we have different parts of this local anesthetics, like a lipophilic center, then ester or amide group, then we have a bridge, then we have hydrophilic center. As we consider the SAR points, each and every center has its important action for the development of the drug molecule as a local anesthetic. As a lipophilic center here, the carbocyclic or heterocyclic molecules considered for the important for diffusion across the membrane. Then we consider the bridges. Bridge should be a shorter carbon chain, and we consider that bridge is having elements like oxygen, nitrogen, or sulfur. And then we have a hydrophilic center. It should have a secondary or tertiary amine and a cyclic or non-cyclic group of member. Most of the time, it should have a long chain, side chain. Now, one by one, we'll see the SAR points of these local anesthetics. The first part is a lipophilic center. As we have already seen, lipophilic center should be carbocyclic or heterocyclic ring molecules, and it is important for the diffusion across the membrane. Lipophilic portion is essential for the local anesthetic activity, as either an aromatic group directly attached to carbonyl function, that is amino ester, or it can be a 2,6-dimethylphenyl group which is attached to carbonyl function group through an NH group, that is amino amide. These groups play an important role in binding of local anesthetic to channel receptor proteins. We have to remember that whenever we consider the lipophilic moiety, this lipophilic moiety in the whole SAR of this local anesthetic, it plays important role for the binding in the receptors. Therefore, for this lipophilic moiety, we need hydro, uh, as you can see, aromatic ring, or it can be a heterocyclic molecule that is important for the fusion. A second important feature, subtle feature we consider here is a ester or amide group that is attached with the bridge. Bridge should be of shorter carbon chain having elements like oxygen, nitrogen, and sulfur. We consider these as an intermediate chain, as it might have ester or amide group in the bridge, and this bridge it is also a resistance, provide resistance for the rapid hydrolysis of the ester and amide groups. This chain almost always contains a shorter chain of 1 to 3 carbons, and the length of this terminal carbon is attached to a lipophilic center, that is aromatic ring or a heterocyclic molecule. Then amino amides are more resistant to metabolic inactivation than amino esters, and having a longer lasting effects. Then smaller alkyl groups around the ester function or the amide function hinders the esterase or the amidase catalyzed hydrolysis and prolonging the duration of action. As this intermediate chain is of ester and amide, we have to remember one thing: we have to make this chain of 1 to 3 compound in such a way that it can resist the metabolic inactivation by the hydrolysis of amide and esters. Then the last moiety here is a hydrophilic center. It should be considered as a secondary or tertiary amine, or it might be cyclic or non-cyclic portion. So this hydrophilic portion is considered as a clinically useful for the local anesthetic activity, majorly having a tertiary alkyl amines, which radially forms water-soluble salts, and it is considered for the suitable of pharmaceutical preparations. The hydrophilic group can be in the form of secondary or tertiary amines, or it can be a part of nitrogen heterocycles. This is how the hydrophilic center it is considered for the action of a local anesthetic, as it have polar moieties like tertiary and secondary amines, and which can be a part of nitrogen heterocycles. As this is one of the example of local anesthetics. Through this example we can see the different types of interaction that can have with the receptor, as we have a first molecule, that is a lipophilic center. Lipophilic center is having a van der Waals forces, or it can be van der Waals and interactions. Then we'll move to the next part, intermediate chain. It is having ester, and the carbonyl group of the ester is having dipole-dipole attraction with the receptor. And then there is a bridge of two carbons. Again, these two carbons provides a kind of lipophilicity to the resistance, as a resistance for this amide and ester. So these two carbons acting as an van der Waals forces through the receptor. Then for the terminal carbon we have a hydrophilic center, and here on this hydrophilic center it is a dialkyl amine, and this dialkyl amine, because of salt formation, it will be now positively charged ion. So when we consider these positively charged ion, similarly on the receptor we will need some kind of forces that can attract the positively charged ions. Therefore it will be electrostatic forces that acts with the positively charged nitrogen. And finally the amines, terminal nitrogen amines, these alkyl groups, they can interact with the receptors through the van der Waals forces. As we consider the interactions here, there are some interactions given for the polarization of these esters. So what will be the effect if we consider electron donors and electron acceptors at the para position of this first lipophilic group? If we consider electron donors, that will increases the polarization of carbonyl group, because these esters, they are considered as they are withdrawing, and they withdraw the electrons from the. Now we consider this OR, it will be electron releasing group at a para position. This electron releasing group will donate its electron, and similarly when it donates its electron to the ring system, the ring system will provide its electron for the stabilization of this carbonyl group, and this carbonyl group will increases the polarization of carbonyl group. Similarly, if we have electron withdrawing group present at para position, the example is a nitro group, and this nitro group will accept the electron from the ring system. So nitro group is one of the unstable group present in the chemistry. This nitro will accept the electron from the ring system. As soon as it started accepting the electrons, the nearby carbonyl group will the oxygen attached to the carbonyl group will donates as lone pair electron towards the carbon, and the carbonyl group will remains uh, unstable. So therefore, if we consider these electron acceptors, this will decrease the polarization of carbonyl group. Now, what is the important part of electron donors and electrons acceptors? If we consider the polarization, it is important for the polarization of carbonyl groups. Let us consider the classification part of this. It is benzoic acid esters. This is a chemical classification as given in your syllabus. Chemical classification. The first class is a benzoic acid esters. The examples given here is cocaine, hexylcane, meprilcane, uh, cyclomethicane, pipriloquine. Then the next class is para-aminobenzoic acid esters. Examples are benzocaine, butambane, procane, butacane, uh, propoxycane, tetracane, binoxynate. The next chemical class is amide or anilide derivatives. The examples are lignocane, lidocaine. It is also known as a xylocaine. All three are named either each other with lignocane or lidocaine or xylocaine. Then mavivecane, prelocaine, etidocaine. Uh, these are the three main chemical classes, and the fourth class is a miscellaneous class. In the miscellaneous class also they have divided as per the chemical moieties present in the drug molecule. Therefore, it is amidine derivative it is considered as a phenacine as an example. Then carbamide derivative example is dipyridocone. Then the next is quinoline derivative. The example here is dibucane. This is a simple classification, chemical classification for the local anesthetics. Let us consider another type of classification, pharmacological classification as per the dosage form. Therefore, if we consider local anesthetics, it may be given in injectable forms, or it may be applied as a surface local anesthetics. In the case of injectables, again they are divided into three different types: shortly acting, intermediate acting, and again long acting. So in short acting we have procaine, chloroprocaine. In intermediate acting we have lignocaine and prelocaine. Again for the long acting local anesthetics we have tetracaine, bupivacaine, dibucaine, ropivacaine, etidocaine. And for surface local anesthetics we consider this lignocaine, cocaine, tetracaine, benzocaine, oxytazine, and propagaine. This is a pharmacological based on doses of drug, that is local anesthetics. And now let us see one by one the drug molecules for this local anesthetics. As the first molecule is a cocaine, and it is obtained from the natural alkaloid isolated from the leaves of Erythrizone coca. Now it is the natural alkaloid, and it is the first drug to be used as a local anesthetic. It is used for the anesthesia for eye, ear, nose, and throat. As you consider, this is the only class having a number of drugs from as compared to other different classes of drugs. So this cocaine, the IPEC nomenclature is 2-methoxycarbonyl tropane 3 benzoate. This is a tropane ring here, and if we compare this, we have 2 esters as in cocaine. I have not given any metabolism of this cocaine, as it is very much lesser considered for this local anesthetics. Uh, the next molecule is hexylkane. It is used as a surface anesthesia, and the IPEC nomenclature of hexylkane is 1-cyclohexyl aminopropane 12 benzoate. Again, it is a type of ester, hexylkane. Our next drug is meprilkane. Here it is used for the dental anesthesia, and we have IPEC nomenclature, that is a 2-methyl 2-propylamino propyl benzoate. Again, this is a type of ester, meprilkane. Next molecule is a cyclomethicane, and if we consider this cyclomethicane, it is of use for the topical anesthesia. As you can see, it have 3 different rings, out of which one is a heterocyclic molecule and one ring is a cyclohexyl. Because of that reason, it has a higher lipophilicity. The IPEC nomenclature for this cyclomethylcane is a 3,2-methyl-1-piperidinial propyl 1-cyclohexyloxy benzoate, cyclomethicane. Our next molecule is a peprocane, and peprocane is considered for the use of ocular anesthesia. It is a very simple molecule. The IPEC nomenclature for peprocane is a 3,2-methyl-1-piperidinial propyl benzoate, 3,2-methyl-1-piperidinial propyl benzoate. It is used for the ocular anesthesia. Our next molecule is a benzocaine. It is used to reduce the pain due to the sunburn, teeth pain, piles, vaginal and rectal irritation. It is a benzocaine, simple molecule. It is derived from a para-aminobenzoic acid, and the IPEC nomenclature of the benzocaine is a ethyl para-aminobenzoate. We have a synthesis of benzocaine also. Benzocaine starts from a paratoluidine with acetic anhydride, and on this we can use the sodium acetate as a salt form. Then it will be converted into 4-methyl acetanilide. Likewise, furthermore, we'll use oxidation and then reduction, and in the last step we will use a simple conversion using the simple acidic conversion. It will form a benzocaine.